Okay, this is for Chem 102. We're going to get started with chapter 14 in this video. So we're going to talk about chemical kinetics in this video, which basically is going over how fast do reactions happen, and then sometimes we'll have to break down the steps in which they happen to figure out how fast they are. So kinetics is what we call the study of how quickly reactions take place. Some happen really quickly. Maybe you've done a chemical reaction in a lab that you see it happen fast, or like you put baking soda in vinegar and those happen really quickly. Some reactions take a long time, millions of years. For example, do you see rust happening immediately? If you just sit there and you watch iron rust, it's not going to be very exciting, but it does happen over time. So increasing the rate of reaction is really important, especially if you are trying to manufacture something in a chemical reaction. You need it to not take years and months, right? You need it to be something that can happen fast. So we need to think about how we can increase the rates of reactions. To understand the rates of reactions, we have to understand how do chemical reactions happen. So collision theory is basically the reaction only occurs when we meet a couple of requirements. So I'm just going to explain them. I think the textbook doesn't do a good job of breaking this down. So for collisions have to happen. Collisions are effective when they are at high enough temperature or high enough energy, right? So high enough energy. If the two reactants collide but not at the right energy, then they won't really do anything. And they are in the right orientation. Let's say incorrect orientation. So we have to hit in the right spot. And we'll look at a video in class that will help you with this idea. So first we have to collide with enough energy and in the right spot. So the rate is proportional to the number of collisions per second. So number of effective collisions, I suppose, or a total number. If you increase the total number of collisions, you also increase the total number of effective collisions. So most reactions happen faster at higher temperatures because we give the particles more energy. If they have enough energy, then they can collide. They also are hitting each other more often, increasing the number of effective collisions. So these effective collisions have to have enough activation energy, and they have to have the correct orientation. So activation energy we'll write as E subscript A for energy of activation. That's the amount of energy that you need to hit at. And then you also have to be oriented in a certain way that favors the reaction. So if I'm trying to get the two chlorines to interact, but if I hit the chlorine on this side, it's not going to react. So you have to hit in the right place and you have to hit with the correct, or at least the minimum amount of energy. And if you have an effective collision, then you get the reaction. So we'll take our single chlorine, reacts with our NaCl, then we get the chlorine taken off, and the NO is what's left over. So again, with chemical reactions, we're really just transferring those atoms around. Maybe you haven't really thought about like what is needed in order for that transfer to happen, but in kinetics, we really dig into that. So ineffective collisions do not result in a chemical reaction, so we can hit all day in the wrong spot. See how we're not hitting in the right spot, and it's just going to bounce off. So we have to have the correct orientation, or if you hit at too low of energy, again, you'll just bounce right off. So when molecules collide in an effective collision, they form what's called an activated complex. You also may hear this called the transition state. So we get this it's like a hybrid between reactants and products. So we have a bond forming between these two chlorines, the green ones, and the bond breaking between the chlorine and the nitrogen here. And so kind of have this what I would draw it as like this halfway bond here and like a halfway bond here. I'm not going to draw the full Lewis structure, but you get the idea that like we're breaking this bond between the Cl and the N and we're making the new bond there. The transition state is really unstable. So if we look at the potential energy, see how it's really high potential energy? Higher potential energy means less stable. Lower potential energy, let me just put it over here. High potential energy means less stable. Low potential energy means more stable. Just like if you were to set your phone on the table versus hold your phone up in the air for the length of this video, right? It's less stable if you hold it up in the air. You're more likely to drop it. So we talked before about this, reactants going to products, like being endothermic versus exothermic, but now we're going to really explore this part, which is the activation energy. So if you have molecules at lower temperatures versus higher temperatures, you will see the higher temperatures molecules have enough energy to exceed that activation energy. And so you'll have more effective collisions for that. So if you increase the kinetic energy, then you'll have more molecules that will, so the number of molecules is increasing this way. And so if the more molecules that you have with the higher kinetic energy, these are going to be the ones that will reach it. So if you have a low kinetic energy, so blue line would be cooler, then you got more molecules at this kinetic energy, and so they won't be able to go over. So we kind of shift our kinetic energy up a little bit. I know this graph, you've seen this graph kind of before, but on its side. But just basically what it's saying is that if you have more energy, you're more likely to get over the hump, which should make sense. So when we're measuring reaction progress, we can express it with a reaction rate. So we have an average reaction rate, which is just really like just the simplest way we can talk about rate. Is the change in concentration. So the brackets mean concentration of substance A. Remember, delta or the triangle means change. So change in concentration over change in time. And for reactants, I put a negative sign in front of this because we're decreasing our amount of reactants over time, and rate is always going to be positive. And so if rate is always positive, if this number winds up being negative because I'm decreasing it, right, then I have to add that negative to make rate positive. So rate number should always be positive, and you could say the rate of disappearance, right, which is still a positive number, but of disappearance for a reactant, or the rate of appearance for a product, again, is still a positive number. So for products, because we're increasing the amount of products, we don't have to put that negative sign. So the rate of the formation of the product is increasing. The rate is also positive. If this is decreasing, it would be negative, and so we got to put another negative in front of it to make it positive. So just remember to put a negative in front of your reactants, then that way you won't get a negative rate when you do any sort of calculation. So we could calculate, okay, if I start at time 0 and I go all the way to the final time, how did A change? That would be my rate for A. Rate of decrease of A, or the rate of the reaction in terms of A. If I start at 0 and I want to see what happened with B, I would look at the difference with how much B we started with, how much B we ended with, and that would be my difference in concentration of B over that time. So essentially it's kind of like a slope. So average reaction rate would be like the number of molecules of A. If I wanted to say like, all right, what's my overall reaction rate between time? Do we have it? Kind of have it here, but let's just do it here. So if I wanted to say in, so if I wanted to know what's the rate from 10 to 30 seconds, like what's the rate there? So we would say the negative change in the concentration of A over the concentration or the change in time. So negative change in concentration of A between 10 and 30 would be 10, I know it's not molar necessarily, but it's 10 molecules to like 23 molecules. So 23 molecules minus 10 molecules over the change in time, which is 30 minus 10. So it's literally rise over run, final minus initial. So this should look like to you y2 minus y1 over x2 minus x1, which is slope, or m, which is rise over run. What we're doing is we're just taking the average rate between these 2 points. But if you can tell just by looking at this graph, this is not a straight line. So it's not going to be perfect, but we can get it as close as we can. In fact, if I were to do from 0 to 60, my line would be much different than if I did, 30 to 40. It follows it a little bit closer. So the smaller that we get in between our points, the more accurate our average rate is going to be. But if we just needed to go from 0 to 60, you can see our line would look a little bit different. So that's how we would plug in those numbers. If you were just given a graph and asked for average rate, you could do it that way. You could also use a table. It's rise over run. It's just slope between the 2 points. So if I have a reaction here, I have bromine reacting with formic acid, I guess that's how we would call this, or methanoic acid, makes bromide, hydrogen ion, and carbon dioxide. The average rate would be the subtracting the reactants of the concentration of the bromine through time. So the final bromine minus the initial bromine concentration, and the final time minus the initial time. So we'd just be looking at our bromine concentration, and we could get that average rate. We could graph it, and then we could look at the graph, or we could actually just calculate, maybe using some sort of spectroscopy, how much bromine is in each of these, and then what's the time difference between these. And we could just do like this one minus this one, or if you wanted to be maybe more correct, you could do all of them and kind of just see if your rate changes through time. So we would measure the absorption of our bromine, meaning we could use like a spectrometer that you shine light through it, and some of that light is absorbed because the bromine has a color. And then you can measure how much it absorbs. So we see that at the beginning it's darker, so it should absorb more. And then towards the end, it absorbs less. And so our initial concentration, so at a certain wavelength, we can find the max absorbance. So different wavelengths of lights are absorbed in different ways. And so if this is orange, perhaps the absorbance is in a certain wavelength, is absorbing a certain color. So we would see, we'd look at the top here, our first concentration at time 1, we have a lot of light being absorbed, so probably high concentrations of bromine. Then as we go to the next time, we see how it drops. And then we go to the next time, we see how it drops. So we could get our overall rate. We can relate absorption to concentration. There's a thing called Beer's law. Ignore the A, the B, but A is for absorption and C is for concentration. So we could figure out, based on the light that it absorbs, there are some other factors, of course, but it's proportionate to the concentration of the thing that's doing the absorption of the light. So that's just how we could measure that. That's one way that we could do that. So let's say I do that and I do this math, I can figure out, hey, here are the different times that I collected data, and here are what my concentrations were. So here are my rates. Between these two, like here was my rate. And then you have your rates for each of these points. And you'll see though, that as we go with our reaction, the rate does not stay the same. So again, when we are doing average reaction rate, again, we're connecting 2 points, and that may not be the exact graph, because as we increase the amount of product or we decrease the amount of the reactant, we actually do change the rate, because the rate is dependent upon how much reactant you have. So think about collision theory. If I don't have as much reactant, they can't collide as often, so the rate will slow down. So the rate actually slows as concentration changes. And so we have to take that into consideration when we're talking about the rates. So if I plot the concentration in bromine over time, I would see concentration goes down over time, but it's not a straight line. We could think about what is the rate at this moment. It would be like this slope, right? So it would be a line like this. But what is the rate at this moment? It would be maybe more like this. So what about the rate at this moment? Well, maybe a little bit more. I know that's way off, more like that. So as you can see, as we go down, we get less steep, right? The rate is the change in the slope of the line. So as the slope of the line gets softer or less steep, that means the rate is slowing down. So as we increase the concentration of bromine, our rate increases. So if we start up here with a lot of bromine and we start decreasing the amount of bromine, my rate is going to go down because it's going to slow down because there aren't as many reactants. If there aren't a lot of reactants, we can't collide. And so it's going to change our rate. So we need to sometimes talk about not just average rate between 2 points, because again, between 2 points is not going to be perfect, but instantaneous rate. The instantaneous rate is the rate for a specific instance in time. So what is the rate at this point in time? So essentially what we want to do is we want to have 2 points that are closer together and measure the slope. This may be familiar to you if you were in calculus. Essentially, we're just taking the derivative of that certain point. So we just want the slope of that exact point right there. And so if we looked at like smaller and smaller and smaller chunks, we can get closer and closer to those rates. So for average rate, if we did just like the first 2 points, we would get a rate. And if we did like the second 2 points, then we would get a rate. But you can see that the change in the first 50 seconds versus the first 100 seconds is not the same. Again, it's not, these are encompassing, and it's not just like double. So it doesn't always change in the exact same way. So what we're looking at for the instantaneous rate is if I change the concentration, how does the rate change? So the concentration at 50 seconds versus the concentration at 250 seconds, there's a ratio here of 2. So 50 seconds is 0.101 and 250 seconds is 0.005, which is almost doubled, right? So there's a ratio of 2 here. And then if you look at the rate at these 2 points, also is a ratio of 2. If your rate, if your concentration changes by a factor of 2, and your rate at those times also changed by a factor of 2, then we can say this is what's called first order. We'll talk about that a little bit later, but we can get ourselves a formula to say, oh, this is a 1-to-1 ratio for the change. The change in concentration, the change in rate are the same. So I would put a little 1 for the concentration. So rate would be equal to a rate constant that changes. Constants only just change proportionality into equal signs. And so as the rate times is 2, the concentration times 2, or vice versa. The concentration times 2, so the rate times 2. So they're directly proportional to each other there. So this is called a rate law, and it tells us kind of how does the rate change when the concentration changes. And they're not all exactly this formula. We're going to talk about how to know what the formulas are in a second, but this is an example of one. So how could we figure out this instantaneous rate? So if we look at, and we can find the rate. So if we know the rate formula, we know this rate law, we can actually plug it in to find the rate constant, which is help us find the rate of any of the other points. So the rate constant we can find by just rearranging, and then we would take 1 point. Maybe let's take 50 seconds is what they use here. So we'll plug in our rate, we'll plug in our concentration, and we get this. Now look at the units. It's molarity per second times molarity. So we, divided by molarity. So we cancel the molarity and we have seconds, inverse seconds. So the rate constant is just whatever units it needs to be to have this all work out according to this rate law, which is the formula. So again, if we're talking about gases, we can get into concentrations, and so those concentrations can we can talk about RT and change in pressure over change in time because the molarity, right, moles over liters, and so we can put those in terms of partial pressures as well. I'm not going to get too much into that. If we need it for an exam or something, I'll make sure to cover it in class. But if you see a homework question about it, we can definitely talk about it more in class. Basically, the reaction rates, if we are not looking at instantaneous, we're looking at more average, we can use what's called a relative reaction rate. So like if I know in a chemical reaction, if I know the rate of disappearance of A, I could actually find the rate also of disappearance of B or appearance of C or appearance of D just using their stoichiometric coefficients. So for this, I'm going to rewrite this so you can see a little bit clearly. So I want you to know the rate for the reactants, we're always going to put that negative. So we've already talked about this a little bit. Change in concentration over change in time. I'm specifically going to open this up and leave a little blank here. It's going to be equal to, the rate is going to be the same no matter what substance we're talking about. For the products, we're not going to add the negative sign because we are forming the products. So they will be increasing. So we don't need to add the negative to counteract that negative change in concentration. But let's say that this was a 2 in front of A. Then A would be going twice as fast as B. So we need to put this 2 where it's going to help us count for the time. So we're going to put it on the bottom of the fraction with the time. So I'll put the A, whatever's in front of the coefficient there, is going to go on the bottom with the time. So same thing for B. So we're going to use these fractions to add to our idea of what a rate expression looks like. And then we can relate it to the stoichiometry. So if the coefficient is 2, that means it's happening twice as fast as something that has a coefficient of 1. And so we put that coefficient on the time side on the bottom to counteract that the fact that it is disappearing or appearing twice as fast or 3 times as fast or whatever the ratio is. So if I wanted to get the rate expression for this equation, and they're showing us here actually. Okay. Let me cover up some of this. We have some space. I guess I could just copy it into a new. Just take this. There we go, that's faster. All right, so if we have our equation here, excuse me, let's write the rate expression. So the rate would be equal to the negative change in concentration of CO2 over change in time. And the coefficient that goes in front of CO2 is 1. So this would just be 1 over 1. Which is equal to negative change in concentration of water over change in time. Now you may be thinking, oh, concentration of water doesn't really make sense, but let's just go with it. 1 over 2, because there is a 2 here. Then we would say positive, or just nothing, concentration of CH3. Now, we're doing concentration here because it's really gases, so they're in concentration with each other. This is not pure because these are gases, they're all mixed together. This one would also be 1 over 1 because the CH4 is a 1. And then this one would be change in concentration of oxygen over change in time, and this one would be 1 over 2 because there's a 2 here. So the water goes away twice as fast as the carbon dioxide, and the oxygen forms twice as fast as the methane, CH4. So see if you can write expressions for each of the following reactions. So pause it and see if you can write them for these. So the next slide, I'll show the answers. So for the first one, you should get, it's the I minus is just 1 over 1. OCl minus is 1 over 1. These should all be 1 over 1. Yeah, so they're just 1 over 1. And so again, I write it like this. I don't write it like out to the side. So you can kind of see what it might look like if you didn't put it like that. I think writing it as an actual fraction is a lot easier to see. For the next one, you should have 2 times delta T because there was a 2 in front of that O3. And you should have 3 times delta T because there was a 3 in front of that O2. For the next one, we should have 4 in front of the delta T because there was 4 in front of NH3. You should have 5 in front of delta T because there was a 5 O2s. We should have 4 in front of delta T because there's 4 NOs. And we should have 6 delta T because there are 6 H2Os. And notice that we're subtracting the reactants. So what can we do with this information? Well, we can write these things, but we can also plug things in and do math with them. At a particular time, nitrogen dioxide, it has a rate of 0.00130. At what rate is oxygen being consumed? And at what rate is dinitrogen pentoxide being produced? Why don't you try it first and then come back? So if we tried this, let's write the rate out first. So the rate is equal to negative 1 over 4 NO2 change in time, negative change in oxygen over change in time, positive 1 over 2 change in N2O5 over change in time. Now, if I want to know about oxygen, we can rearrange this. I'm given information about nitrogen dioxide. I don't need to use all 3 of these. So I can say, well, I know if I pull oxygen out and I want to relate it to the nitrogen dioxide, I write this so that I can get just the oxygen by itself. Well, if I just move this negative sign over, then I get a formula that says the rate for oxygen, which this is the rate for O2 consumption, is equal to, oh, those are both negative. Whoops, I forgot. I wrote it down. So these are both negative, so we can just get rid of the negatives, is equal to 1/4 of the rate of the NO2, because the NO2 is going 4 times as fast as the oxygen. And so if I just plug in this number, 1/4 of 0.00130, that's the rate of the nitrogen dioxide consumption. The oxygen consumption would be 0.00325 molarity per second. So we can do the same thing to the dinitrogen pentoxide. So if I want to know dinitrogen pentoxide, it's 1/2. And this one is positive, and this one is negative. And we know we could use the oxygen too, but let's just use the nitrogen dioxide. In case we got the oxygen wrong, right? If this is part A, we got a part A wrong, we want to make sure we go back and do it this way. So I need to get rid of this 1/2. So how can I get rid of the 1/2? Multiply both sides by 2. So that would give me the rate of production is equal to negative 2 over 4 nitrogen dioxide over the change in time. We know that this is 0.00130 molar per second. So we'll just multiply and divide. Or I know if you know if 2/4 you want to reduce it, you can, or you can just put it into the calculator like that. Um, and the thing about this is that this is the rate of disappearance. So we're gonna kind of ignore the negative there. Um, so we'll assume that I know that's not a negative rate, but we can ignore um, that negative in terms of reporting our number. Because it's just, again, like with endothermic, exothermic, the negative is just showing you if it's going away or if it's being added. So this would be 0.0005. We want to keep 3 sig fig 00 molarity per second rate of production. So this is the rate for N2O5 production. Hopefully that makes sense, but let me know if it doesn't. I got 6.5. What did I do differently? So they use the oxygen. They use the oxygen here and said that the oxygen into O5. Yeah, it would be twice the oxygen. Yeah, I wonder if these numbers are just a little off because they're using the different. I wouldn't have used the 0.1001. It should give you the same thing. Oh, I don't know why. Hopefully you caught that I had made some sort of error there. Should be 0.00065, which is correct. Okay, and why that was different. So when we know basically how the rate is affected by change in concentration, we can write the rate law. We've talked about it already, but we can write it for any of the reactants. We don't really write it for products, but we do write it for the reactants. We just focus on the change in the reactants. So the rate law would be equal to the rate constant times the concentration of each reactant raised to some coefficient, or raised to some exponent. So the exponent is not necessarily coefficient. It is the order with respect to A. And so there are going to be different orders. So we'll talk about orders a little bit later. Next we'll talk about orders. It can be first order, second order, half order, zero order, fifth order. Theoretically, you can have any sort of order. So like like we did this before, right? We said if the rate multiplied by 2, then the concentration that bromine multiplied by 2, that was called first order because the exponent was a 1. But each different reactant can affect the rate in different ways. We call the overall reaction order when we just add up the rates of all the reactants. So how do we do this? So what we do is we have an experiment, and we run this experiment where we change one reactant at a time and see how does that change the rate. So if we look at experiments 1, 2, and 3, let's look at let's look at the F2 first. So the slide next is kind of showing us what the textbook is walking us through, but I want to walk through with you. So which trial would we pick if we wanted to see how fluorine affected the rate? We want to pick one where the fluorine changes, but the chlorine does not. So let's pick 1 and 3. So if we pick 1 and 3, the fluorine changes from 1 to 3. The chlorine does not change from 1 to 3. And so we can see how does the rate change when the fluorine alone changes. So the fluorine changes. What I like to do is if you're not just maybe you can see this change. You can say, oh well, I know this is a times 2 and this is also a times 2, so it does both. But if you're not sure, just take one of your numbers and put it on top and put the other number on the bottom. I like to put my bigger number on top so I get an actual factor. So this is a factor of 2. And then the rates, put the same, if you did the bottom number, so if you did experiment 3 for the top fluorine, you're going to do experiment 3 for the top of the rate as well. So whatever order you put them in. And these are kind of easy to see that, of course, it's going to be 2 because 2.4 divided by 1.2. But if you can't see that in the chart, this is a way for you to do it. So if the formula that we can use here, which is, I don't know if the textbook has this formula, but we can say whatever the change in the rate is, so the change in the rate for the factor that the rate changes, let's call it rate factor. So the rate factor is equal to the concentration factor raised to the order. So we plug that in here. The rate factor is 2. Concentration factor was 2. Raised to the order. What is x here? 2 raised to the what is 2? Well, x would be equal to 1. So that would be called first order. So when we write our rate law, we put a little 1 in, as an exponent for the F2. Why don't you do the same thing for the ClO2? See if you can figure out what order the ClO2 is. All right, so hopefully you tried it out. For ClO2, you see that for ClO2, we see that if we use experiments 1 and 2, the F is constant. The Cl2 multiplied by 4, so its factor was 4. The rate also had a factor of 4. And so the reaction would also be first order, because we would say the rate 4 is equal to 4 raised to the x, and so that would also be first order. So my rate law will be first order with respect to F2 and first order with respect to ClO2, and we don't use any exponents for 1. We would write 2 if it were second order, for example. So I hope that that is helpful. We're going to do more practice with this in class because I want to make sure that you really, really got it. You're welcome to try another example if you'd like this one is another example. So try there. The textbook goes into explanations so you can check your work. And then we will start class with a worked example. Just make sure that you understand a couple things about rate law. We cannot just look at coefficients yet. We'll learn a way in which we can for some cases. Cannot look at coefficients. Rate law can only be determined experimentally. Okay. And we only look at reactants. Right? Each reactant can have a different effect on the rate. So right now we can only find the rate law experimentally. You cannot just use coefficients from a chemical reaction. You got to be given numbers somehow. And then each reactant can change the rate differently. And then we always look at reactants for reaction order and for rate law, not products.